Hello and welcome to the video. And until now, we discussed all the parameters such as large and small signal behaviors and noise in the MOSFET, also the mismatch of MOSFET and all the components and so on. So now it's time to design our op-amps and our circuits using transistor and MOSFETs. So let's quickly review the basic amplifier stages which we have, which are common source, common gate, and common drain configuration. And we know that the constant current biasing is preferred to constant VGS biasing. And because when we do the constant current biasing, so the lower sensitivity of GM demands constant current biasing over constant VGS biasing. So for example, we have biased a MOSFET to constant VGS, and let's say the threshold voltage changes or the mobility of the MOSFET changes due to temperature, and thus the GM will change by a certain amount. And now if we bias with a constant current, then if the threshold voltage or the mobility changes, the GM can change, but the change in GM is very little, as it is biased by a constant current and not biased by a constant VGS. So let's take our simplest form. Let's say that we have a current and which we are mirroring on a MOSFET M1, and we are biasing it using a constant current biasing, and we are providing the V input. So basically, over here we can see the gain as minus GM times R, and the output voltage as minus GM R VI, which will not be affected significantly by changes in threshold voltage or the mobility. And another way of biasing can be basically implementing a current source at the source terminal along with the capacitor, and we can do a GM biasing like this. So these are just a few ways of biasing a circuit. So we are only interested in the small signal performance, and that's why let's just quickly revise the configurations of our amplifiers from our basic analog circuit courses. So we have a common source amplifier, and where we provide the input at the gate, and the output is taken from the drain, and the gain is basically minus GM times RDS parallel R. And as we know, RDS is a very high resistance. So basically, RDS parallel R is nothing but similar to R only. So the gain, we say that it is GM minus GM times R, and that's why we say the gain is minus GM times R over here in this circuit. So for a MOSFET, the output impedance looking in from the drain is RDS, and the input impedance looking in from the gate is basically no current flows through the gate, so it is infinity. So the source is at a fixed potential, and the body or the bulk is also at a fixed potential, and both are small signal grounds. So the VBS is equals to 0, and the effect of body, which is GMV times VBS, is basically 0. So now let's come to our common gate amplifier, where the gate is grounded and the input is given as a current source from the source terminal, and output is nothing but IO flowing from the drain terminal. So what this configuration does is basically it acts as a current buffer with a unity gain, and that's why we say that the I0 flowing from drain equals to the incremental current IN. So basically, it takes potentially bad current source and turns it into a better current source. And over here, we consider that our DS is infinity or GDS equals to 0, and input resistance looking in from the source is 1 upon GM, and the impedance, output impedance looking from drain is, which is basically output resistance, which is infinity. So when RDS is basically not equals to infinity in reality, so R out comes out to be GM RDS times RS plus RDS plus RS, and RS is basically nothing but the source resistor, which is coming with the non-ideal current source. So we will discuss the body effect, and here the bulk is at small signal ground, and the source is not at small signal ground. So VBS is going to carry some value, and if we denote our circles in a small signal picture, so what we have basically is a current source, controlled current source, which is GM due to the VGS. We have GMB due to VBS, and we have our GDS, and this is our input incremental current, and it is provided by the constant VDD through the R. So basically, when we say that, let's call the voltage at this node as Vx, so VGS is nothing but minus Vs, and VBS is also nothing but minus Vx, and these two parallel CCVS can be represented as Gm plus GMB times minus of Vx, and thus the input resistor looking in from the source comes out to be 1 upon Gm plus GMB, where initially it was 1 upon Gm, and assuming that R is not too greater than RDS, so the output resistance looking in from the drain comes out to be Gm plus GMB times RDS times RS plus RDS plus RS. So thus the GMB, or the body effect, is basically helping further in lowering the input resistor or input impedance and increasing the output impedance, and that's what we wanted. So to make a better quality of current source, we basically require a minimal input impedance and maximal output impedance. So now coming to the third configuration, which is common drain amplifier, which is also called as source follower or a voltage buffer, where its functionality is basically giving a V out which is equals to V in but of a better quality, meaning lower series resistance. So let's say we are applying input from the gate and we are taking the output from source, and thus the input impedance looking from the gate is infinity, and input impedance looking from the source is 1 upon Gm, and the gain basically we say that V naught by Vi, the gain is 1, but the condition is RL. So basically this RL, output load, should be infinity, but ideally that's not possible. So our gain comes out to be Gm RL divided by 1 plus Gm RL. So talking about body effect, so when we represented our small signal model, so we have GDS, we have GMVGS, and we have GMB VBS as our source is not at 0, but our ground is at our bulk is at ground. So we have a VBS which causes the body effect, and we know that our GMB is directly proportional to the voltage between the point X and the ground. Also, GMB is connected between point X and point Y, and basically Y is ground. So the controlling nodes of the controlled source, which is GMB times VBS, is same as the nodes between which the nodes between which the control source is connected. So basically these two nodes are the same in which the control source is connected, which is ground and point X. So basically what we can say is that if we have a voltage controlled current source connected between same nodes as a controlling voltage, then it can be represented by an impedance. So this source can basically be represented as a impedance of R, or basically conductance of GMB. So this is how GMB can be represented, because as we say that this source is connected between the same nodes as the controlling voltage. So now when we represented it as a conductance GMB, so now we the transfer function turns out to be GM divided by GM plus GL plus GMB plus GDS. And a GMB can be a significant fraction of GM, but GDS is really small. And the fraction of GM and like we can say that GDS also can be adjusted by the length of the MOSFET, and even with RL equals to infinity and RDS equals to infinity, our transfer function or gain will be lesser than 1 only. So the main consequence of the body effect on common drain is that the gain will always be somewhat less than 1, no matter if we take RL equals to infinity and RDS equals to infinity. So now to reduce this kind of body effect or the attenuation, what we can do is we can realize a common drain using a PMOS, and we know that we dig a N well to make a PMOS. So the body is isolated from other P substrate, or maybe we can say that not isolated, but it is connected to the highest voltage. And since the N well is isolated, we could tie or connect the bulk anywhere we want. So we can say that what if we tie our bulk to the source itself to make the VBS 0. So thus the body effect is avoided. But this brings its own consequences. When we consider the high frequency, as of now, we only consider DC. And now let's consider the parasitic capacitances as well. So let's start with the common drain only. So this is our small signal picture. And we know we have these kind of capacitors, which we already discussed in our previous videos. So we have CGD, CGS, CTB, and CSB. But as because the N well is built on the common P substrate, so there exists a capacitance due to the substrate and the body, and there is a junction between them. So there exists a capacitance which is called as C sub, or we can also call it as C well, which is between the channel and the substrate, and its value can be derived basically by C area, so which is a unit square area times the area of the well plus capacitance due to the perimeter times the perimeter of the well. And we can tie or connect the bulbs to either highest voltage in case of PMOS or to the lowest voltage in case of NMOS. The C sub or the C well does not come into the picture when we do this, as it appears between two fixed voltages. But in this case, where we are connecting our bulb to the source itself, we have to consider that extra capacitance due to the substrate. So let's talk about the parasitics, and let's start with the common drain circuit. So this is a small signal picture of common drain circuit including capacitors, and we can say that let's take RL and CL as the output load, and we'll take our V0 or V output from the source terminal. So assume the bulk is connected to the ground and we apply ideal voltage source as input, so basically DC, and the CDB can be ignored as it appears between small signal grounds, so both ends of CDB is ground. CGD appears across the input and the effect is 0 basically, and CSB can be clubbed or absorbed by CL as it is appearing in parallel with CL. So basically what we have is only CGS, which appears between the gate and the source, and we really have only CSB and CGS to worry about. And now we only have one node, basically this one node, and by applying KCL at that node, we can get this kind of equation where we have differences between voltage. So we have voltage times the conductance SGS plus GM, which is basically equals to the currents going out, which are V0 times GL plus GDS plus SCL plus CSB plus GMB V0, which is basically due to GMB. So our transfer functions comes out to be like this, and we can do a sanity check by saying that consider S equals to 0, then we will get our DC gain, which is exactly same when we derived in the form of DC. So from this, we can say that we are expecting a single zero and a single pole, and intuitively we could have had said that there is only one independent state variable in our circuit, and due to which is occurring due to CGS over here. And we can say that due to that single state variable which is appearing due to CGS, the order of the system is one. Also, there are two parts of the like there are two paths for the input to the output, and one is through the gate source capacitance CGS, and the other path is through the GM. Thus, we also can predict a zero. And when we plot a Bode plot, so basically at very low frequencies, we say that x equals to 0, and we will get whatever the DC gain is. We'll start from here, and then we will occur around a pole P1 whose value is given by some conductance and some capacitance, which we can also derive intuitively. And at very high frequencies, we'll again get a 0, and like the current. So basically what we can expect from the transfer function is at very low frequencies, we say S equals to 0, or the capacitor are absent, or there is open circuit where the capacitors are, and we expect the DC gain. And at high frequencies, the current through the capacitors will dominate over the current through the conductances and transconductances. So this is the value we'll get at higher frequencies. So we can say that as the load capacitance appears in the denominator for larger or heavy capacitive load. So basically, in our transfer function, we see our load capacitance is coming in the denominator. And now for heavier load capacitance, the bandwidth end up reducing. So basically bandwidth is directly proportional to the load capacitance, and for heavy loads the bandwidth will actually reduce. And like alternatively, we can say that to drive a very heavy capacitive load and not to compromise the bandwidth, we need higher value of GM basically in numerator, which means that more power dissipation will occur. So that's how the trade-off is, and how we can like intuitively estimate the value of zero or the pole. So let's take a small signal model again of a common drain. And over here, for poles, so poles are the characteristics of the system itself and not the input and output voltage. So we can set Vi to 0. And firstly, if we set Vi equals to 0, basically to the ground, so at this node, we have CGS and we have CL in parallel. So basically, we can intuitively say that the capacitance in the value of the 0 is basically CGS and CL. So contribution from CGS and CL. Along with that, we can say that we also have the conductances GL, GM, GMB, and GDS. So basically GL, GM, GMB, and GDS at this node. So basically, this is the contribution from the conductances. And of course, the pole is in the negative half plane of S plane. So from these three intuitions, the pole will lie at minus of this value of conductance divided by this value of capacitance. So this is how we can intuitively derive the pole. And for zeros, we check further the paths from input to the output. And here we have two paths from input to output, and first one is like due to Vi minus V0 times SCGS, and the other path is Vi minus V0 times GM. So the first path is basically from SCGS, and another one is due to GM. So the pole is at GM divided by CGS. So alternative logic for this is basically a 0 means the value of S at which the output becomes 0. And so assume that let's assume that output becomes 0. That's where the 0 will occur. So then we have 0 volts across, like when we say that this output is 0 and already the ground is at 0, so we will have 0 volts, not the input, but like if we say that this node is at 0 voltage, then we have our GDS to be 0, our GMB to be 0, our CL to be 0, and our GL as well to be 0, and we have our VBS also equals to 0. So we have current only through the CGS and the GM, and by KCL we can say that GM times VI plus SCGS times VI equals to 0, and thus we can estimate the value of S, which is minus GM by CGS, and that's where our 0 lies, because that's the value of 0, or that's the value of S when our transfer function becomes 0 or output becomes 0. So that's how we can estimate our 0. So now let's talk about the common gate amplifier with parasitics. So where we ground the gate and we have our input incremental current, and we take the output from the drain. So basically, we can very clearly say that our CGD and CDB can be absorbed by CL, and our CGS and CSB can be absorbed as a impedance in parallel with current source. So we can say that our CL prime is CL plus CGD plus CDB, and our CI prime is CGS plus CSB. And if there is a parallel current, like parallel capacitor along with the incremental current source, then let's consider it as CI. So it turns out that the expressions are quite complicated in the presence of GDS, and also they don't lend too much insights because of the value of GDS, which is rather very small, and usually the effect can be ignored. So assume that there is no GDS, and GDS equals to 0. Now we have two independent capacitor loops in our circuit, and due to CI and CL, and there are two independent state variables, thus we are expecting two poles. And for zeros, from input to output, there are only two paths, via GM and via GMB, and then they simply appear in parallel, so they can be clubbed together as a single current voltage controlled voltage source, which is GMB plus GM, and thus we expect two poles and no zeros. So basically the question is, where will be the poles be lying? So let's take node 1, and pole 1 will be lying at the value of inductances associated with this node divided by the capacitances associated with this node. So basically those are nothing but GM plus GMB plus GS, which is the conductances with node 1, and similarly the conductances associated with node 2 is GL, and similarly the capacitances associated with node 1 is CI prime, and that is for P2 is CL prime. So that's how we get our poles P1 and P2, and we can write our transfer function I naught by I input, which is basically our DC gain, which we derived with DC input, and then comes our first pole and second pole. So one of the advantages of common gate is it turns out that the input and output parts are isolated. For example, we have some pole at input and we have some pole at output, and there is really no interaction between these two poles. And now like we know that there is a GDS, but like which causes some coupling. But unlike in other configurations where the common drain has CGS between the input and output, and common source configuration has CGD between input and output, common gate has very like negligible RDS, and it can be ignored anyway. So that's the advantage, and that's how we can call it a current buffer. And now we can look at the common drain PMOS circuit with a bulk to source, like to avoid the body effect and reduce the attenuation, we connect the bulk to the source as we saw earlier, and now we can realize it using the parasitics. So now earlier, when the bulk was to the ground, so when we saw the common drain configuration where the bulk was connected to the ground, our load capacitance came out to be this. But now as the bulk is connected to the source itself, so the output load capacitance comes out to be CL plus CdB, because now dB, so B is not no more connected to the ground, so we have to consider CdB as well, and there is C well due to the substrate. So all the expressions which we derived for common drain are true, just the value of CL will be modified to this equation, and as C well is significantly large, so the bandwidth of the source follower is again related to the CL inversely, and we will have the smaller bandwidth as due to the incremental CL because of C well. And in order to reduce the attenuation, we need to trade off between the bandwidth. So I think this is all for this video. Thank you for watching.